shaped feature here is the cosmic microwave background. It corresponds to photons with a wavelength of about 1 centimeter, the same kind of wavelength as you've got in a microwave cooker at home. Do a first approximation, radiation-wise, the universe is like a gigantic microwave oven, because the energy in this feature is much bigger than that in any other waveband. Moving along, infrared, 3 to 4, these are both infrared. This, number 5, is the optical background, which is the source of Olbers paradox and all that argument that started in 1823. But now, of course, we see that it's only a tiny bit of a much, much bigger spectrum involving all kinds of radiation. So that bit, 5, is what the argument has always been about. Then we get to shorter wavelengths. 6 and 7 both describe ultraviolet observations, which I've been using in order to try and tie down the age of the universe more accurately. Then we get to long, bigger frequencies, shorter wavelengths, 8 X-rays, 9 gamma rays. The point of this graph is that the electromagnetic spectrum, of course, extends indefinitely far from small to large, both in terms of frequency and wavelength. And you get yourselves in all kinds of trouble if you just concentrate on one little bit of it. Let's move on. This is basically a summary of what I've just spoken of. If you imagine that that's us on the Milky Way, photons are coming towards us. If we look backwards far enough, we'll see the galaxies as they were when they were forming, just by the look-back time, the lag effect of the speed of light. So there's a kind of imaginary surface about us, where if we could do it with telescopes, we would see galaxies at formation. In some pencil beams we can see that, but we certainly don't have anything like a total summary of this. The important fact from a philosophical point of view is that already we're seeing a new effect coming in. If the universe has got no center and there's no boundary, then as we go backwards in time, everything that happens must be on some kind of a spherical surface. Okay? Here are the photons coming from places that are so far away that they haven't got time to reach us, a la Olbers. If you can go back far enough, you will see here what I've called images of the Big Bang on a kind of surface. Okay? Technically, that's called the particle horizon. You cannot see any farther. The critical thing about this diagram is a philosophical one. What was an explosion at some critical time in the past, about 13 billion years, is now smeared out, space-wise, into a shell. Okay? This is, in effect, the Big Bang. Okay? It's not a point. Because of the laws of physics, we're forced to conceive of the Big Bang in this fashion. Right? It may be a bit difficult, but you can take it from me. If you practice thinking about it, it'll eventually come easy. So the Big Bang is not really a point and never was. And philosophy, at least, has the usefulness of telling us that if you wish to, you can conceive of it as a spherical shell. This is how people used to think of the Earth in Platonic times, 450 BC. I'm including this to stop us all from getting big-headed. I said that this was the golden age of cosmology, but let's not fool ourselves into thinking that we know everything. The universe right now is supposed to consist, as far as our measurements tell us, of dark energy, photons and neutrinos, not very much of those, cold dark matter, and this bit down here, baryons, is basically the stuff of which the sun and the earth and us in this room are made of. It's the stuff like photons, neutrons, and the nuclei of simple elements, for example, iron and oxygen. Well, this stuff here is only a few percent of the total. The vast majority is up here and in here. The only commonality between what people thought in 450 BC And what people think now is the fact that there are 4 ingredients. Apart from that, the whole picture has changed. So let's not get big-headed and fool ourselves into thinking that we know it all. We certainly don't. If you want a kind of model universe, which for philosophical reasons has always come up in the literature, it's the kind of universe where things start with nothing. So if you were a Buddhist or of that persuasion, you might like that idea. The question then arises, can you have a universe which starts with absolutely nothing, evolves and agrees with observation? The answer to the question is yes. If you're so inclined, you can do that. This t equal to 0 is a conventional description of the Big Bang. I could, if I wanted, run this over to the left-hand side to other values of t. What happens here is in accordance with Einstein's equations, but in a very strange way. It's technically allowable, and I'm showing it to you because there are models by, for example, Bonner in England, who's a well-known relativist of this kind. And if you want something to start from absolutely nothing and then evolve to something, you can do it a la Einstein. What happens is that you start here from nothing. This measures the density. This measures the pressure. The density goes up to a blip, a very sharp rise, because the pressure goes down to negative values. And there has to be conservation. A negative pressure could, for example, be due to turbulence in a fluid. Eddies whizzing around one way or the other tend to pull each other together. If you have a gas like a plasma with particles with positive and negative charges, the particles will tend to pull each other together, even though you may force the whole thing to expand. Again, it's a question of balance. So there's nothing particularly wrong with the concept of a negative pressure. What happens is when you put the negative pressure into Einstein's equations going down there, then the density goes up to a spike. They have to balance. It's Einstein's form of a balance of energies. At the same time, you can plot what happens to the scale factor S in this kind of a model. And what happens is that the whole universe goes through a big blip, the density comes down, then everything comes up, stabilizes. There is a period around here which corresponds to the excess of radiation over matter, and then as it continues to expand, it settles down into a perfectly normal model that is in total agreement with the other ones I showed you on a previous slide. So if you are given to the philosophical idea that you want everything to start from 0, then yes, we can do that if you want us to. You get more idea, though, about what really happens with the Big Bang if you shift your perception. And general relativity traditionally involves the 3 concepts of space, x, y, and z, and the concept of time, 4 dimensions. What happens if you add another one? You can do that either as a matter of fact or as a matter of imagination. And I'll leave it up to you to decide which point of view you want to take. But if you do that and embed our 4-dimensional universe in something with a higher dimension, this is what you get for the standard model. So it starts at something that looks like a point, it expands. These lines, transversely and longitudinally, tell you about the ordinary space and time locations. However, we've now plotted it in a different kind of setup with a length L, a new time t, and a new radius r. It's symmetric around r equal to 0. So the whole thing evolves with the shape of what is actually a parabola. So this is a 5-dimensional plot of a 4-dimensional real universe. And it helps us because now we can see exactly what the Big Bang is. It will correspond to that point. However, the rest of the space is nothing complicated about it at all. It's just flat and empty. If you want a model like that, but which accelerates with time, according to what cosmologists call the inflationary model, then you can have that as well. Here, though, the shape is not parabolic, but it expands with a trumpet shape, okay? So you've still got a situation way back in the past where things originated, but now it involves this typical trumpet-shaped device at the end. At some point, you have to ask yourself whether we do in fact believe in all our equations. Like, do we really believe in our equations or do we not? Of course, I believe in them because I spend my livelihood doing them. And the fact that somebody pays me to do it, I suppose is lucky, but it also implies to me that other people believe in them.